All right, so welcome to the software design track and welcome to this particular talk about breaking dependencies, type erasure, a design analysis. So before we get started, give me 10 seconds to introduce myself. My name is Klaus Iglberger and I'm perfectly okay if you stick to the first name because I realized many people cannot pronounce my last name. So I'm Klaus and I'm actually working as a C++ trainer consultant. And so the topic I've chosen today is one of my favorite topics because it's actually indeed about dependencies, which I perfectly feel is one of the most important things to talk about, software design. And yes, there is many talks on type erasure out there. Many good speakers have given talks and really good talks. However, many of these talks very, very quickly dive into implementation details. Very quickly are lost into the tiniest details how to implement type erasure. Virtually none of these talks is talking about the thing that I feel is most interesting, why type erasure actually helps you to break dependencies. And from a software design point of view, this is actually the most important aspect. So this is what I want to do in this talk. Against your expectation, however, I will not directly jump into type erasure. I'll actually first very quickly talk about the challenge of software design in general. Then we'll solve a problem very naively by just using inheritance. Then we improve the solution. You reach for a couple of design patterns. And then we finally, last but not least, go into type erasure. The goal of my talk, however, is that after this talk, you should have a very good idea about type erasure, not about every single implementation detail. This is what I leave away, but about why this is something that you should be interested in from a design perspective. And also you should have a pretty good idea which design patterns are actually happening, which design patterns we use in order to make all of this magic work. So let's start with the challenge of software design in general, because I believe this is actually indeed super important. If you develop software, you're always facing problems. But interesting, all of these problems have to do with change. They all have to do with change. If we wouldn't have to change things, if everything would already work, then, well, we would be fine, absolutely. But change is what actually makes us realize that there's something imperfect. And this is actually something that is expected. Software must be adaptable to frequent changes. That is the reason why software is called software in the first place. It is supposed to be easy to change. It's supposed to be adaptable to whatever changes I want to do. However, it's not that simple. If it would be, probably it would not be that interesting. But indeed, it's often very, very hard to change things. And indeed, these difficulties that you may experience very often lead back to any kind of dependencies. Dependencies between software entities. Dependencies that make you change, that make you apply a change, but then change something else, and perhaps something else again. And sometimes it's not even obvious why you have to change other things. That really makes things difficult. Difficult to understand, difficult to change, and difficult to maintain. And that's exactly what we want to talk about. It shouldn't be that hard. There shouldn't be many dependencies. You want to break them in order to be able to change things easily and in order to have a nice and comfortable career. So, one quote by Ken Beck: "Dependency is the key problem in software development at all scales." It really is something that we have to address. And that's what we are doing. Let's start with a naive solution to a very, very well-known problem. We are dealing with shapes. And I know at this point already, at least 20% of the people are exiting the talk, are logging out. It's a boring topic, a boring example. And yes and no, but actually in my test talk, I asked what example should I use? And we discussed this for quite some time. And in the end, it was still shapes. So to put it in the words of my co-organizer from the Munich C++ user group, I'm tired of this example, but I don't know any better one. So, shapes it is. We're dealing with shapes, but please don't pay attention to shapes at all. It's just the motivation. We want to create a couple of dependencies, and that's the important aspect. So, I'm starting with a naive approach, and I'm starting with a shape base class. and we want to draw shapes. Now, of course, there's many shapes, circles, squares, and you can imagine that there's also a couple of more interesting ones like ellipses, rectangles, and whatnot. All of these classes now would have to implement draw, simply because in the base class it's a pure virtual function. But that is something that very, very quickly might actually lead to problems. The circle class now implements draw itself, and therefore it suddenly is coupled to implementation details that it actually should know about. For instance, these implementation details might actually be bound to OpenGL, VTK, 3DX, any big graphic library. And so this tiny geometric primitive circle suddenly depends on a graphics library. That definitely shouldn't be. That doesn't feel right. And also, obviously, we now have one implementation and one only, say OpenGL. But we might want to have many implementations, OpenGL and 3DX and any other graphics library. And again, a naive solution is to just inherit again. So let not the circle implement draw, but deriving classes, OpenGL circle, metal circle, 3DX circle. They might implement draw in many, many different ways. Hey, problem solved. Yeah, okay. We also have to do this on the square side, of course, because the square also needs to draw somehow. Well, it's not beautiful, but it actually might work for some time. But software changes. Requirements change. And so perhaps a few months later, suddenly there's the requirement to actually also serialize shapes. So to turn them into some byte pattern, in order to store them in a database or in some file. So we need to serialize shapes. Now, serialize also is something that has dependencies on how we actually want to serialize. Do we use little endian or big endian? Do we use that format or the other format? There's many possibilities again. And also, there's the same problem. Where do we actually implement that? And again, the naive solution is to just inherit once more. So now we have the OpenGL little endian square and the OpenGL big endian square, and you might imagine a couple more. Ooh, the names already start to look like something that you do not like. And also, very important, this hierarchy is starting to grow. The depth is growing, and you might imagine that there's a third function. It is growing to an extent that very quickly you actually don't understand anymore. Perhaps there is the approach that you just limit the size. So a circle acts as some base class, it's still abstract, but then you immediately implement all of the combinations. But it's also not beautiful. The name is definitely not, and there's a lot of duplication. A lot of duplication indeed, because OpenGL now appears in two implementations, which definitely is not what you want to have. So, in other words, the naive approach doesn't work well, not at all. So, using inheritance naively to solve a problem very easily, quickly leads to many derived classes, which we don't like, ridiculous class names. I don't know if you like them, but I definitely do not like them. Deep inheritance hierarchies, which is a problem indeed, because very quickly people don't understand this anymore. Duplication, now perhaps we get it under control somehow, but it's a hard thing. And it's suddenly really, really hard to go further. A third function, a fourth function, it simply doesn't work well anymore. And of course, in the long run, your maintenance is in danger. You might not be able to add anything anymore easily, and so you might start to use workarounds. And workaround already sounds like a bad idea indeed. Well, as the pragmatic programmers said, inheritance is rarely the answer. Delegate to services. Heisei trumps essay. And that's exactly the attitude of our next approach. Let's move towards design patterns. Let's actually use the solutions that we traditionally have used for many, many years, if not decades. And of course, I'm now reaching for this book, Design Patterns, Elements of Reusable Object-Oriented Software, the so-called Gang of Four book, short GOF book. That book is the origin of 23 of the most commonly used design patterns. Now, As I've explained a couple of days ago, I think 2 days ago, I don't consider all of the patterns in here really design patterns, but that's a different story. But just as a recap, a design pattern has a name. With that name, you communicate intent. So what do you want to do? What do you try to do? How do you consider your code to evolve for the future, of course? And all of these design patterns should aim for some kind of reducing dependencies. Somehow they try to manage the interaction between different entities in software by introducing some sort of abstraction. Yes, in that book, it's usually some kind of base class, but generally speaking, it doesn't have to be a base class. You can also use templates, different approaches. Any kind of abstraction is fine. And the last point, a design pattern definitely has proven to work over the years. That doesn't fall from the sky. A design pattern is something that definitely has appeared in many code bases and always posed a specific kind of solution. The design pattern I now reach for is the so-called strategy design pattern, which for our purposes is just the right thing. So we have this circle class that implements draw. And our problem is that the circle contains these draw implementation details. That's the problem. I don't want circle to implement draw itself. I want to extract these details. And that usually is the first step for design pattern. You have something that couples too strongly, you have something that potentially changes, and that variation point, that aspect is extracted. Okay, and traditionally by means of some kind of base class. I forgot to mention that this circle is, of course, a representative of any concrete shape. Could be a square too, could be the ellipsis, the rectangle, of course. Now, we extract the drawing aspect. I call this draw strategy. That draw strategy is now the representative of drawing itself. By means of this base class, I can now implement it in various ways. But most importantly, I do not inherit from circle anymore. I now build on composition. On a has a relationship. A circle has a strategy. Usually, traditionally, this is done by means of a pointer to base. That pointer to base can be injected, dependency injection, so a circle truly is not depending on any concrete implementation anymore. So draw strategy can now be implemented. Comment again. So that is exactly what the single responsibility principle wants us to do. Extracting and isolating the thing that varies, the thing that changes. And that enables us now to implement all kinds of strategies. OpenGL, VTK, 3DX, Metal Vulkan, you name it, your favorite library, you can now implement this easily by just adding new code. That's essentially what the open close principle tells us we should do. If that's what we need, that's how extension should work. It also enables us to test, some test strategy, which is definitely what we might desire. Sometimes we don't want to draw, we just want to see that everything works. Testability is improved as well. All right, this is now the design pattern that we apply. And this design pattern, first of all, I should definitely mention, is not limited to object-oriented programming. It's also not limited to dynamic polymorphism, and it's not a language-specific idiom that always works in exactly that way. No. The strategy design pattern is something that you can apply in many, many forms. So, as a little detour, allow me just to point out that it definitely also works in templates. The accumulate algorithm. You can, if you want to, replace the strategy here, how you want to accumulate. You could use a multiplies too, if this is what you need. You can combine with logical AND or bitwise AND, whatever you need. That fourth template parameter is actually a strategy. You provide the algorithm to make accumulate do the right thing. But a vector, a standard vector, has also a strategy. It's allocator. You can decide how exactly the allocation should work. You are empowered to specify that detail on your own by dependency injection. Of course, that is true for all containers. And an unordered set has even 3 strategies: a hash, a key equal, and an allocator. All of these allow you to specify details of how the unordered set works. It's a template strategy. And last but not least, unique pointer, simply because we'll use it now a couple of times, also uses a strategy. Its deleter is something that you can provide at compile time, but that is some aspect that you can configure from the outside. So it's a dependency injection indeed. So just to point out, strategy is not something that we now use just in the form that the Gang of Four gave it to us many years ago. There's many different ways of using that, many more forms. But now we apply this to our drawing shapes example. Now the shape base class is exactly as I've described it before. It comes with a pure virtual draw and a pure virtual serialize function. Any deriving class now needs to implement these. But as I said before, we definitely do not want to directly implement these. We do not want to couple on the implementation details. This is why, for the draw aspect, that should be enough to explain it, we introduce strategy classes, a draw circle strategy. That class can have any virtual functions, so I'd now name it draw as well, gets a circle and of course a couple of additional arguments for drawing. Some kind of appearance, color, etc. That should be enough. And now the circle class is adapted accordingly. A circle is a shape. For that reason, we need a draw, we need a serialize. But again, we don't want to implement this on our own. In this implementation, in the constructor, I now get a unique pointer to a draw circle strategy. So I get a unique pointer, which makes it clear I will take the responsibility for this particular base class. Great, because then the lifetime questions have been answered already. I now move that strategy into my data member, which is of course a unique pointer to draw strategy. And whenever somebody calls draw, I don't do this work myself, but I forward the request. I call the draw function on my strategy, pass myself, forward all the arguments, and I'm drawn. That works. And this is why I am not depending anymore. I've broken the dependencies on these implementation details. I don't have to know anything about drawing anymore. Still, you do realize that I still have a draw function. I still know that I can be drawn, which might not be what you have in mind still. So we can more strongly decouple, just not with this pattern. Okay, and then just to make it complete, of course, we need another draw strategy for square. And yes, indeed, we need another class, else we artificially couple circle and square together. That must not happen. So I need another base class, draw square strategy, basically the same thing as before, and square is implemented in terms of the draw square strategy. In a constructor, potentially also setter, I get a unique pointer to draw square strategy. I move it into my data member, and I use that whenever draw is called. All right, then I'm suddenly in the position to implement this in various ways. So an OpenGL circle strategy or an OpenGL square strategy. I can implement this anywhere else. I don't have to depend on these things. And in the main function, I just put it together. I create a couple of strategies. I create a circle, give it the according strategy, add it to some vector of unique pointers of shape, for instance. Something. Interesting is that I am now indeed empowered to very quickly adapt strategies. If you want to, for instance, invisible squares, you can change that here. Square doesn't have to know about that at all. You have broken the dependency indeed. Great. So we have managed dependencies, and that is what design patterns usually do. We now indeed have 3 levels in our architecture. We have something that I would call high level, the stable things, the things that we want to build on, and that high level contains the shape, the base class. Then there's some kind of medium layer, intermediate layer. This is where we implement circle and the according draw circle strategy. And now that enables us to implement different strategies on another low layer. A layer where all the implementation details can reside, a layer that we consider to be malleable, volatile, well, the implementation details. So the higher we are, the more abstract, the lower we are, the more we see that the implementation details. Okay, we definitely have won something. So we have used the strategy design pattern to extract implementation details based on the single responsibility principle. We have created the opportunity for easy extension, and we have separated interfaces, which is nice. So circles, squares definitely still don't know about each other. That's the so-called interface segregation principle. Also, we have now a very, very clever way of dealing with duplication. There's only one implementation. We don't have to think about this anymore. It's so obvious. And also, big win from my point of view, we have limited the implementation hierarchy's depth. There's a circle, and then we extract this and we have a new hierarchy. Definitely much better than understanding one big hierarchy with 10 different levels. Nobody would understand that anymore. And so I claim we have definitely simplified maintenance. It's easier. It's easier to handle, easier to write, and definitely easier to understand. However, it's better. It's not perfect. I would say there is a couple of details that are not okay, not perfect yet. First of all, performance. If you're a performance aficionado, you're probably very unhappy right now because definitely performance is reduced due to a second indirection. Yeah, so my strategy class has another virtual function. Draw was virtual, but now I have a second virtual function due to the draw function in the strategy function, strategy class. 2 indirections in order to draw a shape. That may be unfortunate. Performance is also reduced since I have many, many small allocations. Every one of my shapes, my base class, in my main function, just a few seconds ago, was allocated individually, manually, and also all the strategies were allocated by Make Unique. A lot of tiny allocations just to make it work. Then performance is affected due to many pointers as well. Many pointers, many indirections. That is definitely not super fast. But then, apart from performance, you might have realized that actually this is not the end of it. There's draw. Okay, we solved that. But there may be more functions, serialize, and potentially many more. And I need a strategy class for all of these operations. And yes, I should actually have a separate base class, else I'm, again, artificially coupling aspects. So I'm suddenly started base classes all over the place. Yeah, the proliferation of base classes, strategy classes. I also need to manage lifetimes explicitly. It works. We have unique pointer, but it's not beautiful. And okay, this is what I just said. And still, it's a personal opinion perhaps, but still a circle, a square, etc. knows about drawing, knows about serialization. Logically, it does not know about the implementation details anymore, but still all the operations are somehow bound to shapes. And that's something I believe we could and should optimize. Now, and there is a better solution. A solution that actually achieves exactly the same thing from a dependency point of view, but even better. And there's a solution that does the same thing as strategy, but also actually solves the lower aspects. And that now, of course, is type erasure. So I do assume that you've heard about this before. And you might have heard about this before from this talk, Inheritance is the base class of evil, which actually, to my knowledge, is the first public talk about that topic, although this was admittedly super quick. 24 minutes. Actually, Jean officially had 20 minutes. And so he squeezed first ranting on inheritance and then the type erasure solution into 20 minutes. It's a fabulous talk indeed, but super fast. Yeah, you probably have to watch it twice in order to be able to follow all the details. Because that is such an early talk, because it may be the first one, many people attribute type erasure to Jean, or at least the group at Adobe. But actually, no, there is something much, much earlier. The earliest mentioning of that technique, not under that name, but definitely exactly that implementation is from a paper from 2000. The author was Kevlin Henney. And in that paper called Valued Conversions, he actually describes a std_any. Pretty much exactly the thing that we're using today. He already described in 2000. And by that, I believe he could be named the inventor of type erasure. He didn't name it that way, but at least to my best knowledge, I do him the favor and call him the inventor. Type erasure. As I said, you might have heard about this before. You may have, for that reason, also many different ideas what that truly is. So allow me to give you a couple of ideas what type erasure is not. Type erasure is not a void pointer. True, we don't know the type of the thing anymore. But that's a ridiculous technique. That's not something that we need to name explicitly. It's also not just the pointer to base. The thing that we've now seen a couple of times, yeah. We have a base pointer, potentially as a unique pointer, pointing to some implementation. No, also not type erasure. And also type erasure is not a std variant. From a design perspective, std variant is actually the exact opposite of what we are trying to do here. Standard variant is based on a closed set of types and gives you an open set of operations. What we are now trying to do is to have an open set of types, but a closed set of operations. So indeed, it's exactly the opposite. So no, we don't want to use the same terminology, the same name for something fundamentally different. Type erasure is, in short, a templated constructor plus a completely non-virtual interface plus a very clever combination of three design patterns, namely external polymorphism, bridge, and prototype. And that's now what we are taking a look at. And I'm pretty sure already that you will start smiling very, very soon. Very soon indeed. And that smile will not go away for the rest of the day, I promise you. It is fascinating if you think about the dependency aspects. All right, we start with a circle class. And no, I will not change this anymore. This is what circle is in the end. Just a geometric primitive, nothing more. That circle does not know anything anymore about drawing, about serialization, about any other operation that you might come up with. And of course, the same is true for square. They don't need to know anything special. There is no base class. More, perhaps importantly, they don't know about each other. Separate classes, circle and square, are different geometric primitives. And most importantly, perhaps, they don't know about their operations. What will be done on them later? That is already pretty beautiful. You do not have to go back to circles and squares and add operations. Nope. They actually may be finished, they may be used pretty much everywhere and pose no dependencies whatsoever. Yeah, and this is a promise. We'll not change them anymore. What we'll now do is we actually employ a very, very clever design pattern. I'll now introduce two structs. And yes, I'll make them structs because actually I don't want to encapsulate anything here. And quickly you will realize that indeed it's not necessary. So just two structs. A shape concept, which is implemented as a base class. So we have a virtual destructor and a shape model. Shape model is a class template that inherits from shape concept publicly. The word that I now omitted, unfortunately. Shape model has a constructor. It takes a T. A circle, this could be a circle, this could be a square, this could be anything. It takes something and it actually uses that. It should move in that case. It should be a forwarding reference also. Now this is a R-value reference. Either way, it takes some circle, it takes some square, whatever. Now, the shape class, the shape concept class now takes all the operations that I need. Serialize, draw, anything that I actually might need for my circles, my shapes later. So this is again the two pure virtual functions that before were in the shape base class, which doesn't exist anymore. These operations are now implemented in the shape model. In the shape model, I now have implementations of these classes, of these two functions, but Again, I don't implement them on my own. I again forward. I now explicitly state that whatever I have, whatever my object is, I now expect this object here to have a draw function and a serialize function. So whatever I get, whatever I store, must have a draw, must have a serialize. And this is now basically the definition of the operations that I truly expect on the given type. I now specifically expect free functions, just because this, of course, helps you to much more cut dependencies. So this is basically the definition of the real affordances, the real operations that I expect on T. All right. I said this is a very clever design pattern. This structure, this external hierarchy that allows you to basically store anything, that is called the external polymorphism design pattern. That is a design pattern that is not so well known, unfortunately, because it's not part of the Gang of Four book, but it was actually published in 1996 by Chris Leland, Douglas Schmidt, and Timothy Harrison. The intent of external polymorphism is stated right in the beginning of the paper: allow C++ classes unrelated by inheritance and/or having no virtual methods to be treated polymorphically. These unrelated classes can be treated in a common manner by software that uses them. So that design pattern is basically about externalizing the polymorphism. So you may have an int, but by means of that design pattern, you can actually deal with this int polymorphically. You can add the polymorphic behavior separately, which is indeed absolutely fascinating. And as we'll see in a bit, from my point of view, one of the most important design patterns that we have today. But unfortunately, it's not that well known. So we definitely should publish this a little better. This external polymorphism design pattern allows us to treat any object polymorphically. Not the object needs to have virtual functions. We can add them separately in that external hierarchy. It definitely helps us to extract implementation details, and it definitely removes dependencies to affordances. My choice of using free functions helps me to really reduce the dependencies on the given types. Now, of course, you can expect member functions too, but this would that would ask for more coupling, of course. We create the opportunity for easy extension. We can now add a rectangle, an ellipsis, easily. We don't have to add anything to them, or we can even use third-party code. This might just plug in very quickly. And yeah, absolutely a very nice list of advantages. Now, this is the external polymorphism design again, which we now just extend with the operation that we need. A free serialize and a free draw for both circle and square. And of course, so first, this is what we require. This is what we need. But there's not one implementation. There can be many implementations. So there can be many files, headers, source files that now implement different versions for serialize and draw. And of course, they should be separated too. Now, serialize and draw don't have to be in the same file. Definitely not. You can now decide by means of the right include, by means of linking the right library, which functionality is actually used. You're actually in a very comfortable position here to easily change what you need. Okay. At this point, we would simply still draw, and I skip that. Let's go to the main function. We would, at this point, create shape models of circle and a shape model of square, for instance. We could initialize them in some way, put them in this vector. It would work. However, we're not happy. We're definitely not happy yet. Because still, there is a lot of make uniques. There's a lot of things that we do have to do manually, pointers all over the place, virtual functions, etc., etc. So that external polymorphism design pattern alone is not what we need. Now, let's combine this with a little more. Let's combine this with a class. we now put this hierarchy, this artificially added library, into the private section of a shape class. Now, perhaps it's a little more obvious why I used struct before. Now it's private anyway. This shape class now takes all the responsibilities to manage the things that we've actually before had to deal with ourselves. Creating things by make unique, for instance, by dealing with things, lifetime management, etc., etc. This class now has a templated constructor. Shape has a templated constructor which may take a constant ref or a forwarding reference, again, whatever you want. As I said, implementation details are not so important for me today. And that constructor, when you call it, will create and instantiate the right model for you. So you pass a circle. T may be a circle. I instantiate shape model for circle. Then put the right thing inside and store that in form of a unique pointer to base. Of course, my base is a shape concept. So I create the right kind of model. I store it, however, by means of a pointer to base. And by doing that, I essentially have lost the information what I truly store. I don't know that anymore. Might have been a circle, might have been a square, but I don't know that anymore. That gives this, by the way, the name type erasure. I've erased the type. I don't see the type in the interface of the shape class anymore. I don't see it anywhere. It's primarily gone. But because we have this nice base class, of course, we can still use the right thing because we have virtual functions. We can go back there. Indeed, pretty fascinating. And this here is, in fact, the second design pattern at play. This templated constructor creates a specific instantiation of shape model. And we store it by pointer to base. That is the bridge design pattern. That is, again, one of these classic Gang of Four design patterns. But it's not just the pimple idiom that you may know from C++. That now is a real bridge. There is one base class and there's many, many derived classes. And in our case, because of this templated constructor, virtually an infinite amount of derived classes. The beauty is we don't have to write them. The compiler will generate them for us, which, as we'll see in a bit, from a dependency point of view, is the best thing that could ever happen to us. Perfect use of a template, class template in this case. All right, we now add a couple of extra functions. If you have a serialize and a draw function for circles and for squares, then the shape class should also have these functions. However, at the same time, these functions need access to this pimple. So I have now implemented these two as friend functions inside the class. And if you've not seen this before, don't worry. So this is free functions. I could implement them outside and add a friend declaration. This is kind of the shortcut, which is a little nicer for the presentation. Now, slideware. But still, I now have exactly the interface that I expect on my types myself. You can now draw a shape, you can serialize a shape. And of course, the shape now is this abstract thing. So if you call draw on a shape, the shape will simply call the according draw function of the shape concept, the virtual function, and then of course the one from a shape model. That now draws the function, calls the draw function that will in the end draw the circle, draw the square, whatever you store inside. So you reach out to the virtual functions and it works. This is how you get back to the real thing. Now, of course, we also need the special member functions. We actually don't really need move in the sense of we can default the move operations. That's beautiful, that's easy. That's because we stored unique pointer. But we actually have to deal with copy. Now that one appears to be a challenge. All we store is a pointer to base. Now you want to copy something that actually not really know how to copy this thing. Not because it doesn't know what it truly stores. That is interesting, but there is a very nice, a very clever solution. We can add, now it's here. Now we can add clone functions to both the base class, the shape concept class, and the shape model. That is the so-called prototype design pattern. The clone function will return a copy of whatever is stored in the derived class. Yeah, and will return a copy in form of a unique pointer to shape concept. That clone function is implemented in the derived class. And here it's simple to implement because we know exactly what we are. We have a very clear idea what we need to do. We need to copy ourselves. So we copy ourselves. So we pass this to the copy constructor. We allocate another shape model, return it by means of pointer to base. And so we do have a copy. And that's all we need in order to implement a copy constructor and a copy assignment operator. Now we can ask in an abstract form, give me a copy. Perfect. So we now manage this thing indeed in form of a value. We've just implemented a value wrapper. We can copy that thing, we can move that thing. We don't even have to remember that it actually stores some kind of abstraction inside. A beautiful value indeed. A type erased value. All right, the usage is now a little nicer. So if you want to draw, you simply call a draw function. And creating that is actually super beautiful indeed. So you might have a vector of shapes. This is now values. We don't need any pointers anymore. And we can now simply create circles, squares, etc. directly. Now we put all of this inside this vector and we erase the type. Now we can now traverse an entire vector and draw them in an abstract form. It pretty much acts like the strategy design pattern that we've seen before, but in a much, much nicer way. All right, let's take a look at the design overview. Again, I have 3 levels in my design. So this is already an indication that apparently it's the same thing again. On the high level, I have the abstraction, which is now my shape wrapper type. That is the class with the templated constructor, the class with the unique pointer to base, the pimple, and of course the class with these 2 structs inside. That is my abstraction. One level below, I assume, because that makes sense, I have circles, squares, and all the other shapes. These, interestingly, do not have to know anything about the shape class on the higher level. They're totally independent. So they could even be on an even higher level. They're totally independent. But, of course, at some point I now need to combine these. And that happens in, for instance, the draw implementation. In that implementation, I now bring all of these things together. I fulfill the requirement of shape to have a draw function, and I also, of course, use circles. So in my low level, I finally combine all of this knowledge. And that, of course, happens by means of this template. Shape model. The shape model is instantiated for every particular kind of shape. So I have a shape model for square, I have a shape model for circle. That is the code that the compiler generates for us. That now builds the glue between the abstraction and the concrete implementation. But we don't have to write this on our own. We don't have to. For that reason, we have now super loose coupling. And that indeed makes this absolutely superior to any classic inheritance hierarchy. There is virtually no strong dependency anymore. Absolutely fascinating indeed. So fascinating that I now quote Eric Niebler, who blogged about this in June 2020. And he apparently also seems to be pretty happy about that. If I could go back in time and had the power to change C++, rather than adding virtual functions, I would add language support for type erasure and concepts. Define a single type concept, automatically generate a type erasing wrapper for it. And yes, he basically expresses what many, many people feel. It's absolutely amazing from a design perspective. But it's super frustrating that we have to always write this wrapper class for it. And that is something that the language should give to us. That would make it easy. And then virtually all inheritance hierarchies could be replaced by something that is much, much stronger from a decoupling point of view and something that is much more beautiful to use later. So the technique is indeed beautiful. Just a little unfortunate that we have to write so much code in order to make it work. All right. So indeed, amazing job. To summarize, we have used type erasure to extract implementation details. Definitely. We have created the opportunity for easy extension. Definitely. Now we can add circles, not circles, but rectangles, ellipses very, very easily. Loose coupling indeed. We have still very, very separated interfaces. Hardly anything knows about something else. We have properly dealt with duplication, very, very elegantly so. We have pretty much removed all dependencies to operations. Circles, squares, etc. do not have to know about drawing, serialization, etc. anymore. Super elegant indeed. And there's no inheritance hierarchies left. There is one. Yes, but it's inside the private section of the shape class, the wrapper class, which is something that officially we don't know about. Yeah? So we don't have to deal with inheritance anymore. There's no pointers. We have values, which is something that in C++ we definitely like much better than any kind of pointers reference semantics. There's hardly any manual allocation that we have to do. Inside we still do something, but again, this is somewhere in the wrapper. And we have manually managed all lifetime very, very nicely, easily. And interestingly, we have also improved performance, or at least there is the potential. Now, this is exactly where I refer you to all the other talks, because indeed there is many, many talks. Talks that, for instance, explain that you could easily add some kind of storage policy. How should I allocate the things inside? Should I use new? Should I have a small buffer that stores things? There is plenty of optimization opportunity. Just a side note, yes, that's a strategy. There is many talks. So, for instance, Zach Lane talked about this. Arthur Dwyer gave an introduction talk, still shows a couple of things that he can do to optimize. Cy Brandt and Eduardo Madrid are definitely two people that have a lot of ideas how to optimize the code. There is indeed a lot that they can do. I should also point out that Eduardo will give another talk about type erasure tomorrow, Friday. The talk is called Large Performance Gains by Data Orientation Design Principles Made Practical Through Generic Programming Components. So, one idea, one thing that you can do as soon as you have embraced this type erasure idea. And indeed, I guess that will show that there is a lot to gain from a performance perspective. Now, of course, you're asking, is there something that I can use in order to make my life easier? Or do I have to implement all of this stuff? No, there is libraries available. The Zoo library, that is Eduardo's library. There is Dino, a library implemented by Louis Dion. And there is also Boost type erasure. And there may be even several different kinds of type erasure libraries inside Boost. That is probably the most generic one, the one that you can use the one that allows you to most easily adapt it to your likings. Okay, and of course there's more. I apologize if I did not get all of the libraries that are available. So as a summary, type erasure is a templated constructor plus a completely non-virtual interface, thanks to the external polymorphism pattern that we use inside, but also a very, very clever combination of three classic design patterns. An external polymorphism, no, it's not a GOF pattern, but still it's pretty old, 1996. We use bridge and we use prototype. And I believe indeed type erasure itself is some kind of design pattern. Yes, the primary design aspect is what external polymorphism gives us, but this nice encapsulation in form of a value type is indeed something that we like a lot in C++. And therefore, This itself helps a lot with managing dependencies in a very elegant way. Okay, type erasure significantly reduces dependencies, enables value semantics, improves performance, improves readability and comprehensibility, eases maintenance, and is for that reason, as of course all of these 5 points are super important for everyone. And of course, for that, it's a very good reason that other program languages use that pretty extensively by default. In C++, unfortunately, we have to do this manually. And so again, yes, it would be nice if we would have this in the language. Perhaps someday. All right. So I've seen there's a lot of questions. I'll try to address as many as possible, and we have a couple of minutes left. All right, slide 54. Let me go back to 54. Okay. Takes a little time. 55, 50. Sorry, it's a little slow. We'll get there eventually. 54. So, why use friend functions in a shape type instead of public methods? If I use public methods, public serialize and a public draw, then I don't offer the same interface that I expect from circles and squares. So if I expect circles and squares to have free functions, I should also offer the same interface for generic purposes, of course. That's why I do prefer friend functions. Sure, you can, of course, add a couple of public functions, but still, you should have the free functions to mimic the other interface. That's what I did in one step. Okay. Feel free to additionally add something. What are the trade-offs of using type erasure to enforce a closed set of operations as opposed to C+20 concepts? I think it's a different thing. You could use a concept, for instance, exactly at this point in order to check at compile time that the thing that you're adding is a shape, whatever I now understand as shape. And from my perspective, a shape is something that I can draw and serialize. You could use a concept here to check at compile time the properties, but this is dynamic polymorphism, pure dynamic polymorphism. A concept is static polymorphism. You can combine them, you can strengthen the entire thing by using both, but it's not a replacement. Still, if you do have a compile time problem, then please use a compile time solution. Concepts are your thing. That is if you have any kind of dynamic polymorphism problem, a runtime problem. Okay, I hope this answers the question. Is it possible to support member functions or free functions? Yes, absolutely. It is your choice. You decide. I believe this is back a couple of slides. Let me go back here. Yeah. You decide at this point what exactly you consider to, what you require. This is what T needs to support. A T needs to have a free draw and a free serialize. You can also at this point call a member function. Then the T requires a member function. But you can go one step further and you can say, well, if it has a free function, I'll use that one. If it doesn't have a free function, I'll look for a member function and use that one. And if it doesn't have both, perhaps you have a fallback, but then perhaps it would be an error. There's a lot that you can do simply because you've wrapped this up and you now are free to implement this as you like. It's loose coupling indeed. All right. Bugado asks, if drawing needs to acquire a resource, who owns it? Okay, I guess this is still related to the strategy example. I'm not quite sure. So in a strategy example, the unique pointer expressed the RAI idea. The RAI idea is that the resource is handled automatically. A unique pointer does that. As soon as I have this shape class, this wrapper class, I can decide how exactly I deal with this the resource. I can use a unique pointer again. I can use a little serial buffer, a static buffer, I mean. It is your choice again. you can manage the lifetime as you seem fit. You can also store the thing as you seem fit. And by the way, a little static buffer inside the class can actually give you a lot of performance increase, indeed. That's something like a small buffer optimization. But again, I refer you to other talks about that. All right. Alessandro asks, once a shape is type erased, is there a way to reach the actual type, for example, to get the radius of the circle or the width, height of the rectangle? That is a good question. Not easily. It's exactly the same problem that you have if you have a base class, pointer to shape, what we had in the beginning. No, it's not easy to go back. In an inheritance hierarchy, this is what we call a downcast. For a downcast, what you usually have to do is to either use a static cast, which is dangerous because, well, it might not be a circle. You believe it's a circle, but it might be a square. Dangerous. Or you could use a dynamic cast. That is safe, but expensive. Here it's exactly the same problem. You cannot easily go back. Once you store this in a shape, it's gone. Of course, what you can do, and I say can do, you can, of course, add something to go back. That is what standard function, for instance, has to some extent. But experience shows this is not a particularly good idea because you now immediately couple to RTTI information to enable that, and that makes things much slower and more, a little bloated. Not a good idea. So if you use that technique, there is no desire to go back. You don't want to go to get the radius of a circle anymore. Okay, hopefully this answers the question. David asks, does anyone use some command line tool to generate those? It should probably be relatively straightforward to create them from some interface specification. That is a good idea. I'm just not aware of anybody who does that already. But it is a good idea indeed. And I would use such a tool because it would be so valuable. What I've just presented is generally a replacement for any inheritance hierarchy. And of course, any tool that could do that for you is super welcome. So perhaps you have a new hobby. All right. Aaron asks, why does shape model need a base class? That is a pretty good but pretty important question. I go back. Sorry, I have to find the right slide. I go back here. Perhaps even some of this is that whereas affordances. This is let's stick to this. So you create some shape model yourself or it is generated, but then of course you want to store it inside the class. Inside shape, I need to store the thing that I got. I cannot store a shape model though, a shape model of T, because the T is only known in the constructor. And this is what I was looking for, the constructor. Let me go forward, perhaps I find it again, I do hope so. But unfortunately, this makes it a little slow. One more. So now I introduce the class and add the constructor. So at this point, I create the shape model of T. The T is known here in the constructor, but not outside. So outside this constructor, I couldn't store that. I needed a base class in order to be able to store it at some point. Super important indeed. Without that base class, you wouldn't be able to keep it. Yeah, so here, I store a unique pointer to a shape concept, base class. I could not store a shape model at this point. If that's not clear, please talk to me afterwards. All right, and one more, a short one perhaps. So yes, I will definitely publish the slides. Definitely, they will be published. Generally, all the slides will be, hopefully all the slides that are presented at CppCon will be available at some point. Okay, so Julian asks, last question. It is a bit unfortunate in this example that the same objects needs to know about drawing and serializing. All right, I believe that this is actually something that we now solved with type erasure. I believe that this is something that might have been a question from before for strategy. But still, yes. Also in the type erasure solution, there is still a dependency, but only in abstraction. This abstraction is shape abstraction. Now says, I need for all the shapes, draw and serialize. Circles and squares don't need to know about this anymore. That's the bonus, but still you just combine all the operations that you expect on a shape. That is the abstraction, the semantic abstraction. So no, it's not perfect. I don't claim this is the one solution that you now use for everything henceforth, but still, we decoupled a little more strongly. So if the answer was not sufficient, please ask me again in GatherTown. And this is now what I'll do. I close the session officially. Thank you very much for the attention. I hope it was valuable for you. And if there's more questions, I will now in half a minute be in GatherTown, and I'll try to answer all the other questions that you might have. So thank you very much, and enjoy the rest of the conference.